Hello there guys, today we are going to be solving IB Physics HL Paper 2. Let's jump right in, shall we? Question number 1. This is our mechanics question as is standard with IB Paper 2. Our first question is always mechanics and it's generally extremely hard, so this time actually it's not. So consider yourself lucky if you actually get a paper like this in your exam session, M23 students. So let's go ahead. A raindrop falls vertically from rest. We're looking for the initial acceleration of the raindrop. So we all know that the raindrop will initially be in free fall before air resistance acts on it. So it's going to have an initial acceleration 9.8 meter per second squared. And that is going to be our answer for this first question. So moving on to our next question. Explain by reference to the vertical forces how a raindrop reaches a constant speed. Now, for this particular question, I say we take a look at our graph up here. So we see that the speed initially increases here and then suddenly levels off around 2 seconds, I guess. So that should give you a representation. So as the raindrop falls, the component of weight is constant, but air resistance continuously increases until it becomes equivalent to the downward force by weight. And then once these are equivalent, your F net becomes 0. So A net becomes 0, which means V is equal to constant. And that's about it. So when we write this out in words, we have to keep a few things in mind. First of all, we have to make sure that we're writing out the fact that the raindrop is accelerating downwards. So downwards. After that, two forces act upon it, gravitational force and drag. So this drag acts in the opposite direction, upwards, and while gravity is initially greater than drag, the speed increases, but eventually air resistance will become equal to the gravitational force, so the net acceleration will become 0, resulting in a constant speed of the raindrop. And so just make sure you explain it to the best of your ability. I mean, this kind of a diagram makes a lot of sense, but putting it into words is important, and making sure you have your key terms is also very, very important. So let's move on to our next question. Part C. During the first 3 seconds of motion, the raindrop falls a distance of 21 meters and reaches a speed of 9 meters per second. This is the mass of the raindrop, and the temperature does not change, which is not important for IB, but if you're really looking at it, temperature could change the density and such. So determine the energy transferred to the air during the first 3 seconds of motion. So the energy transferred to the air is essentially going to be the loss of energy. So loss of energy is going to be, it's going to be our initial PE minus the final KE, because we'll just assume that since it's falling a distance of 21 meters, here we only have potential energy and here we only have kinetic energy. So keeping that in mind, let's go ahead and write this out. So this is going to be mg delta H minus K, which is half m into V squared. Now, so in paper 2 especially, I like to write out all the numbers in the beginning. This is something that my teacher taught me and really impressioned upon all of us, because it makes sure that we're showing the examiners exactly what we know, and we're saying, hey, I know all of this. So we can go ahead and write out delta H is equal to 21 meters, M is equal to 34 into 10 power minus 6 kilograms. Make sure to keep your units consistent, guys. After that, we're looking for velocity, which is equal to 9 meter per second. And finally, we are looking at G, which is going to be 9.8 meter per second squared. So now I know all of you guys know that paper 2 is a paper in which you can use your graphics calculator. So I hope you all have it out to simplify a lot of these calculations. So let's plug in our values. 34 into 10 power minus 6 times 9.8 meter per second squared times delta H, which is 21 meters, minus half, where the mass is 34 into 10 power minus 6 kilograms, into V squared, which is 81. Now let's first find our potential energy, which is 34 10 power minus 6 into 9.8 into 21. This is going to be 6.9972 into 10 power minus 3 joules. And this, now let's look for a kinetic energy, 0.5 times 34 into 10 power minus 6 times 81. And this is 1.377 into 10 power minus 3 joules. Now taking the difference between both, we can just subtract the first value minus a second, and we get the answer as 5.62 into 10 power minus 3 joules. Of course, your calculator may show more significant values, but seeing as we only have 2 SF to every single value, we can say delta E is equal to 5.6 into 10 to the power of minus 3 joules. Now, make sure to keep in mind your significant figures at all times, guys, because examiners may mark you very critically based on that. And just write out 2SF. Now, moving on to our next question. Describe the energy change that takes place for t greater than 3 seconds. Now, we have to go back to the graph for this one. Here, we see that the speed is increasing. At about 2 seconds, it levels off, but at 3 seconds, it's absolutely dead straight. So, keeping that in mind, this means that no energy is transferred. Not no energy transferred, but PE does not directly become KE anymore. Instead, we are losing energy to the air, like how we calculated in C part 1. So let's just say that the graph shows that delta V is equal to 0 at t greater than 3 seconds. Now I'm using shorthand because I'm showing you guys, but in your exam, make sure to use the actual words. And therefore, all gravitational potential energy is converted into thermal energy in the air. Now, since we are given a key term in the question, energy change, make sure you include thermal energy and gravitational potential energy as part of your answer, because those are key terms the examiner is going to be looking for during the correction process. Moving on to question number 2, we have an energy question. So, on a certain day, the intensity of solar radiation is 680 watts per meter squared, and if you remember, intensity is equal to power by area. So that is going to be useful later on in our paper. So later on the questions rather. And we are given a range of values, slew of values. So we are going to have to answer our questions using these values. Part 1 asks us to determine the minimum area of solar heating to increase the temperature of all the water by 30 degrees Celsius, not by 230 degrees, from our initial value of 15 degrees Celsius in 1 hour. So for this, we can use our specific heat capacity formula. E is equal to mc delta T. Now, this means that we will find the energy required to raise it. But we are given intensity over here. But I'll get to that in a minute. So first of all, let's go ahead and plug in our values. M is equal to, and since the values are given here, I'm not going to write it out this time. So let's directly plug in our values. So 250 kilograms into 4,200 joules per kilogram per Kelvin into 30 minus 15. Now this is equal to 15,750 kilojoules. Not joules, guys, kilojoules over here. And I'm just simplifying this from the calculator, so should be fine. Yes. Now, we have to look at the power. So power is equal to energy by time. And we are given our time of 1 hour, which is equal to 60 minutes, which is equal to 3,600 seconds. So we can use that. But you should remember that we have an efficiency as well. The efficiency is given as 0.3, which means a 30% efficiency. Now, this means that if we were to rewrite this, our energy input would be the power into time. And since we have an area, of course, since we have an intensity, we can write intensity into area into time. And we have an efficiency as well, so let's write that out, efficiency. So intensity is 680 watts per meter squared. Sorry, wrong capitalization. Watts per meter squared. And then we have an area, which we are told to find. So area, and then we have a time, which is 1 hour. So 3,600 seconds, because 1 watt is equal to 1 joule per second. And finally, we have our efficiency, which is 0.3. So we need 15,750 into 10 power 3 joules is equal to 0.3 times 680 times 3,600. So, oops. $86,400 into 10 power, 86,400 A. So now simplifying this, we get A is equal to, so 15,750 into 10 power 3 divided by 86,400. Oops, messed up a value previously. So we're not looking at 86,000, guys. If you were following along with your calculator, you might have noticed. Sorry about that. It is 734,400 A. This means that A is equal to 21.4 meters squared. And since all of our values are to two significant figures, we write A is equal to 21 meters squared. And that's it. Now let's go ahead to part 2, which is in which we are estimating the temperature of the tiles. So here you need to remember that albedo is equal to the reflected energy by the incident energy. So that means that the absorbed energy can be written as 1 minus alpha times input. Since 1 minus alpha, so I'm just going to derive this on the side, guys. Since 1 minus alpha is equal to incident minus reflected by incident, which is equal to absorbed by the incident. Since anything that's not absorbed is going to be reflected, so anything that's not reflected is going to be absorbed. So this is one derivation that you guys have to keep in mind while practicing, solving papers, whatever. So now using this formula, which we've converted from, we can write in our values. So we have 1 minus 0.2 is our albedo, right? Yep, 0.2 is our albedo. And we have to multiply it by the input wattage, which is 680 watts, 680 watts per meter squared. So this means that we have 0.8 times 680, which is 544 watts per meter squared, is absorbed by tiles. Now, since we have an area and a power, so P by A, so let's use another equation from our data booklet chapter 8. P is equal to A E sigma T power 4 A. And we are given an intensity, right? So that's P by A, like I mentioned above. We get E, sorry, I've written rho, E sigma T power 4 is equal to P by A. So this means that T is going to be, I'll write that next to it, save some space. T is equal to the fourth root of intensity by emissivity times the Stefan-Boltzmann constant. Now, these are all values in your data booklet, and your emissivity of the roof tiles is given over here, 0.97. So, temperature is equal to the fourth root of 544 by 0.97 times 5.67 into 10 power minus 8. This means that our temperature is going to be 315 Kelvin. So if we just input that in our calculator, I believe, yes, 544 by 0.97 times 5.67, 10 power minus 8. Beautiful, 315.36, but we're going to round that up to 315 Kelvin. Now, since we are looking for temperature in Celsius, we need to subtract 273.15. So 315 minus 273.15 is going to give us 42.21 degrees Celsius. And of course, to two significant figures, 42 degrees Celsius. That's it. Moving on to our next question, part B. We are asked, state one way where a real gas differs from an ideal gas. The intermolecular forces in a real gas are non-negligible. This means that when we look at van der Waals forces and things of the like, you will not be able to follow the exact law PV is equal to nRT. Now you might be able to write that out as well. Real gases do not obey PV equals nRT exactly, so on. But this is just one of the many answers that you can give, guys. So here, this is a water tank that we've been calculating the previous question. So we'll give an opening, airspace, and water. Now, the airspace is always constant at atmospheric pressure and at constant volume, while the water level is kept the same. So P is equal to constant and V is equal to constant. And the airspace temperature and water temperature are the same. So that means T air is equal to TW. They're not saying that the temperature of air is constant. They are saying that the temperature of the air is equal to the temperature of the water. So I've just put our answer in here. So we are using the equation PV is equal to nRT. And we are given that the temperature is constant and the amount of water in moles is going to be constant at any particular temperature. But what is also constant is the volume, which is proportional to the temperature. But here's the thing, this is volume of the gas, not volume of the container. Remember that. So since we're considering the volume of the gas here, PV is equal to nRT and V is equal to nRT by P. So P is directly proportional to temperature. As temperature increases, the volume of a gas increases, which means that some gas must escape because otherwise the pressure will increase. But since it's constant atmospheric pressure, since P is equal to P atmospheric pressure always. So you guys have to write this out in a little bit more elegant manner, not scribble all over the place like I have, but this is as good of an explanation as any. So moving on to part C, we are asked to compare photovoltaic cells and a solar heating panel. Now this is pretty obvious. Photovoltaic cells emit, or output rather, not emit, key terms guys, output electricity, while solar heating panels output thermal energy. Now, of course, this is the most straightforward answer for the difference between a photovoltaic cell and electrical cell. But Of course, you can have many other answers, like the output of a photovoltaic cells can be stored, while the output of a solar heating panel can't exactly be stored because you don't have a heat battery, do you? So let's go ahead and move on to question number 3. A string of length 0.8 meters is fixed at both ends. Standing wave is formed, and we are given two particles, P and Q. The variation with time to displacement of P is shown here. So let's just mark that as P. Now we are asked to draw the variation of T with the displacement of particle Q. Now if you look at it, Q does not have the same maximum amplitude as P. You guys know that in standing waves, this is the amount that a particular particle will resonate or will oscillate. So this means that Q is going to have a lower amplitude than A. And additionally, you can see that it's out of phase with P. It's on the opposite side. So I'm going to draw it perfectly out of phase. In reality, it might not be perfectly out of phase, but that's what we're going to keep over here. And let's just say the amplitude is 1 for ease of drawing. So I'm marking out my points. I marked out all of them. And let's try to draw a smooth curve. I am not the best at this, as you guys may have seen in my previous math videos, but you get the point. A curve is formed where the maxima is lower than P and the minimas are higher than P, and it is exactly out of phase. Moving on, we are asked to calculate the speed of waves on the string. Now looking at this, we can see that this entire setup is the third harmonic. So for third harmonic, we know that the length is equal to 3 lambda by 2. And if you don't want to memorize these formulas, you can just look at it. This is 1 lambda from this end of the wave to this end, and here you have another half lambda. So the total is going to be 3 lambda by 2. That's a very simple way to remember it, so if you guys need to use that, much easier. So 3 lambda by 2 is equal to 0.8 meters, since we are given the length is 0.8 meters. This means that lambda is equal to 1.6 by 3 meters. And now we are asked to calculate the speed. And you can only get the speed when you have a time, right? So let's look for the time period of a wave. That's going to be 2.8 milliseconds. This is where I really test you guys. You need to be able to look at information from all parts of the question, not just the text, not just the diagrams, combine them both. So time period is equal to 2.8 milliseconds, which is equal to 2.8 into 10 power minus 3 seconds. So V is equal to lambda by T, which is equal to 1.6 by 8.4 into 10 power minus 3, which is equal to 16 by 84 into 10 to the power of 3, which is equal to 16 by 84 to 10 power 3. And we are given a speed of 190.476 meter per second, which we round off to 190 meter per second. And what is this? Of course, two significant figures, as always. 2SF. Now, let's move on to the next question. I think we've actually powered through these questions much faster than paper 1, which is pretty good. So, in paper 2, you have a lot more time. So, you don't have to go super fast, not as fast as paper 1 at least, but make sure to keep a steady pace. If you get stuck on a question, skip it, come back to it afterwards, and always leave time for checking. So now we are given part B. It suggested that the speed c of waves is related to the tension, where tension is equal to AC squared. Now, an actual formula for this is V is equal to root over T by mu, where mu is the linear density of the string, but that's not required in IB. So let's leave that out for now. So tension is equal to AC squared. So let's perform something called dimensional analysis for this. Or instead we can just say we have to equate the units on both sides. So tension is a force which is equal to mass times acceleration, which is kilograms meter per second squared. Correct? Now C is a speed, which is meter per second. but since we have c squared, the unit is meters squared per second squared. Now let's compare the two, shall we? Kilograms meter per second squared is equal to A times meter squared second inverse squared. You see the seconds just neatly cancel out, and one of the meters cancel out. So kilograms is equal to A times M. So A is going to have the unit of kilograms meters inverse. And that's it. Now, if any of you know the dimensional formula, which is mlt power minus 2 is equal to A times m squared t power minus 2. You could also do it the same way, but you'd get the same result either way. But this is the method that IB uses, so just go ahead with that. Moving on to part 2. The tension force on the string is doubled. So T is equal to AC squared, T dash is equal to 2T. Describe the effect, if any, on the change of frequency in the standing waves. Now, if you guys remember, since this is c squared, 2t is equal to a c dash whole squared. Now, if you were to look at it in the beginning, we'd say c is equal to root over t by a. Correct. But now if we look at it here, c dash is equal to 2t by a, root over 2t by a. And so c dash is equal to root 2 into c. So therefore, speed increases, not decreases guys, increases by a factor of square root of 2. Moving on to C part 1. The standing wave creates a traveling sound wave in the surrounding air. Outline one difference between a standing and traveling wave. Easy peasy guys. Traveling waves transfer energy. Meanwhile, when we're looking at standing waves, they do not. Now again, this is only one of many differences. You've seen that this is almost the third question where we have a simple difference question. So know your theory, know your definitions, know this stuff, because it actually is very helpful. Of course, we could also say that the amplitude of oscillation varies along a standing wave, but it's constant in a traveling, or that nodes form in a standing wave while travelings don't. There's so many. So just stick to one, make sure you know it well, and write it down very clearly. Moving on to part 2 of this question. The speed of sound in air is 340 meters per second, and in water it's 1500 meters per second. So we have to discuss whether the sound wave can enter the water or not. So I'm just going to write everything out and then explain it so that it's pretty easy to understand. Okay, so here we are looking for the refractive index of air, which I'm going to represent with eta. And for that, we can use the formula is equal to, refractive index is equal to V by V media by V air. So that's going to be 1500 by 340. Now this gives us a refractive index, so we're just going to leave it at that for now. And we can use the critical angle formula, which is 1 by sine C is equal to refractive index. So here we can write C as theta C is equal to sine inverse of refractive index, which is 340 by 1500. Because we are reciprocating the value, we need to reciprocate this as well. So this means that theta C is equal to 13.1 degrees. Now we see here that the wave direction is 30 degrees. Now this means that the angle of incidence, theta I, is greater than theta C, which means that the wave will not enter the medium. That's it. So make it simple, make sure your equations are shown very clearly, and make sure that you're actually using numbers that justifies every part of it. That's about it. Moving on to question 4 actually. So a mass is attached to one end of the rod and made to rotate in a vertical circle. Remember that, guys. The scale diagram shows the weight W of the mass at an instant where the rod is horizontal, and we have to draw an arrow to represent the force exerted on the mass by the rod. Now, this is actually a pretty interesting question. Since we are, so I'll use a different color here. Let's pick pink. So since the weight is acting downwards and it is still attached to the rod, it means that the rod must provide a component of its reaction force that is directly opposite, and it will provide a force like that. That's perfectly vertical. Next, we have to look at centripetal force, Fc. So Fc is provided this way, as always. And for this particular thing, I'm just going to draw it as 3 units. It could be anything, your choice. Since as long as it's acting this way, inwards towards the center of the rod, you are good. So now let's draw our vector. Starting here and going down here, we have our arrow, our final arrow, that's going to be like this, F. And that's it. So in your exam, I would suggest erasing these so that the examiner doesn't get confused and can clearly mark you. But for this, I will leave them on. Moving on to the next part. Explain why the magnitude of force exerted on the mass by the rod is not constant, sorry. So when we look at this, the magnitude of force exerted on the mass by the rod. So I'm going to draw it out first, and then I will show you how to write it. So let's consider these 3 positions: position A, position B, and position C. Now, we all know that centripetal force always acts this way. So I'm going to draw it in green, Fc. And it's going to have a constant magnitude. Fc is equal to mv squared by r. And v is constant because it's constant speed, and m and r are obviously constant. Now, let's look at what's varying. We use a different color for this. The mass, so the weight, mg. That's going to be here, this much. And over here, it acts along Fc. And here it acts in the opposite direction of centripetal force. Now this means at different points, the tension in the rod, let's use dark green, tension in the rod is going to be varying. So at point A, our tension is going to be equal to, Fc is our constant, correct? So that's provided by the tension in the string plus or minus, or plus in this case, the weight. Now you guys should remember that Fc is actually a pseudo force, which means that it doesn't actually exist like gravity or friction. Instead, it's provided by other forces. In this case, gravity. So keeping that in mind, we say that Fc is equal to T plus mg. So this means that the tension in the rod is equal to centripetal force minus the weight of the block. Let's look at position B. So we already know that at position B, the two vectors are oppositely inclined. So for this, we can say that the force acts something like this. So I'm going to ignore point B because it's a little bit long and the math is not exactly required for a simple question like this. But if we look at part C, we see that the centripetal force is actually equal to the tension minus the weight. This is because the tension acts upwards while the weight acts downwards. So by the sign convention, we know that they must be subtracted from each other to give centripetal force. Now, this is what makes it interesting. This means that tension is equal to centripetal force plus the weight, which means that tension at C is greater than tension at A, which is why the tension or magnitude of force exerted on the rod is not constant. So, if you were to write this down, there are a bunch of key points that you have to keep in mind. Our first thing is the force is a reaction force to the mass. Next, we have to point out that at the bottom, or here, the gravity opposes Fc. So the tension, or the reaction force must increase. And at the top, the magnitude of tension is equal to Fc minus mg. And at the bottom, it's plus mg, like we wrote up here. So this gives us a few formulas, and we have to say that Fc is a constant term, but the direction of mg in relation to Fc is changing, which means that the magnitude of force exerted by the rod is always changing. And that's it. So let's go ahead and move on to the next question. Question number 5. A resistor is connected with a cell that has internal resistance. State what is meant by an ideal voltmeter. Now this is a purely theory-based question, and an ideal voltmeter must be connected in parallel and must have an infinite resistance. So an ideal voltmeter possesses infinite resistance to minimize the current flowing through it. Instead, you only get voltage that's flowing through. Next, the resistance of R is 50 ohms. The voltmeter reads 1.47. We are asked to calculate the current in the resistor. Very simple. Ohm's law, V is equal to IR. I is equal to V by R is equal to 1.47 divided by 50, which is equal to 0.0294 amps. But we are asked in milliamps. This means that the current is equal to 29.4 milliamps. Now remember guys, we have to keep it to 3 significant figures because we have 3 here and we have 3 here. So I will remember to write that 23SF. And that's it. Next, resistor R is replaced by another resistor of resistance 10 ohms. The ammeter now reads 139 milliamps. Show that the internal resistance of the cell is about 0.7 ohms. So this is a fun one guys. So here we're going to be using the formula EMF is equal to current resistance plus internal resistance. So since the EMF is never going to be changing, neither is the internal resistance, we can equate two equations. We can create a set of simultaneous equations and we can solve from there. But instead of that, we are given almost everything. Only internal resistance is not given. We are given, so let's go ahead and write it out first. Current 1 times resistance 1 plus internal resistance is equal to current 2 times resistance 2 plus internal resistance. So we are given current 2, current 1, resistance 1 and resistance 2. So we have everything we need to solve this question. So let's go ahead. 29.4 milliamps times resistance 1, which is 50 ohms, plus the internal resistance is equal to 139 milliamps times 10 plus internal resistance. Now you might be wondering, why didn't I write into 10 power minus 3 at here and here? That is because since both sides, if we deal with milliamps, we end up with millivolts, which essentially cancel out anyways. So I'm going to remove the 10 power minus 3 on both sides because, like I said, they will just cancel out. Now, when we expand this, we will get 1470 plus 29.4 R is equal to 1390 plus 139 R. This gives us 80 is equal to 109.6 R, which means that the resistance R is equal to 0.73 ohms, which is approximately equal to 0.7 ohms. Now box the whole thing because we are given a lot of significant figures here. So, I've actually not written the correct number of significant figures. So 80 divided by 109.6. So it'll be 0.7299, which actually does down to 0.730. And that is approximately 0.7 ohms. And we can write here, hence proven. Make sure not to go outside the box, guys, because examiners can only read what's inside the box. Literally, it gets cut off on their screen before they see anything else. So keep that in mind right inside the box. Now for the final step of this equation, EMF of the cell. So to calculate the EMF of the cell, you take the same formula that we used before. EMF is equal to current times resistance plus internal resistance, and just straight up substitute that in. 29.4 into 10 power minus 3, 50 plus 0.73. EMF is equal to 1.491 volts. But since we are given 3 significant figures everywhere, we're going to write it out. EMF is equal to 1.49 volts. And make sure to write 23SF. Now, of course, you can limit this to 2SF, but don't worry about that. We'll keep it at 3 because that is the correct number of significant figures for this calculation. Moving on to C part 1, explain by reference to charge carriers in the wire how the magnetic force on the wire arises. Now this is a pretty big writing question, so I'm going to copy paste into this. Okay, so I've written out the answer over here, guys. So the magnetic force is exerted on the charge carriers in the wire, which are moving with a velocity. By F is equal to BVQ, a force is exerted on moving charges, and this force translates to the wire, causing the force on the wire. Now this is just basic electromagnetic force. So very simple, make sure that you write out a formula so that you can say, hey, there's a justified reason, and as such, a force is exerted. That's it. And of course, we should not forget to mention that the moving charges produce a magnetic field in themselves. And this field interacts with our external magnetic field. that's it. Now I did just add this point on in the end, that's why it's going on to over here, but like I said before, please do not do that. It could end very badly for you. You might end up losing a mark, 2 marks, and you never want to be in the position where you lose a 7 by just 1 mark, guys. So make sure to keep your writing in the box or ask for an additional sheet from your teacher. Now, a very simple question. Identify the direction of the magnetic force on the wire. Now, I like to remember both the Fleming's right hand and left hand rule. Right hand for a motor and left hand for a generator. And by the right hand rule, we see that the force is going to be our thumb. The magnetic field is going to be our index finger. And since the current is going this way, if you were to try to move your hand into it, you'll see that the thumb actually goes into the plane of page. So this is our magnetic field, this is our force, or this is our current, sorry, and this will be our force. So excuse my chicken-handed kind of drawing of my hand, but I guess this works. So magnetic field is this way, current is this way, and as such your force is going to be into the plane of paper. So go ahead and write into the plane of paper. So moving on to question number 6, we are told about a nucleus and we are asked to explain why the mass of the nucleus is less than the sum of the masses, referring to the nuclear binding energy. So I've written this answer out and let's go ahead and highlight the key points. First of all, we're mentioning exactly what force is being used, which is the strong nuclear force, because within the nucleus, the strong nuclear force is what holds together the individual nucleons, keeping it from essentially scattering into space. Next, we are mentioning exactly what this is. It is called binding energy, and it's provided by what we call the mass defect. Now, the key point here is the equivalence of mass and energy, saying that the mass is different because of this binding energy. So, using this formula, E is equal to mc squared, the small amount of mass is lost, and that is equivalent to the energy required to break the nucleus apart. And you could also say this is equivalent to the energy required to, let's say, keep the nucleus together. Keep nucleus together. But of course, it doesn't really matter because the amount of energy required to break it apart is the same as the amount that's required to hold it together. And that's about it. It's a 2-mark question. Make sure you get your key terms and points in, and that's about it. Let's move on. Question number 6b. Calculate in mega electron volts the energy released in this decay. So what you'll see here is we are given values in U, the atomic mass unit, but we need to convert that to electron volts. And the conversion for this is 1 U is equal to 931.5 mega electron volts. And you'll find this in your data booklet, so don't worry about it. So let's go ahead and jump right into the question. Since we're looking at the energy released in the decay, let's go ahead and write it out first. So we have polonium 210 decays into lead 206 plus an alpha particle, which is 42. Now, with this in mind, we can simply take the energy in the reactants and the energy in the products, subtract them from each other, and find the energy released. So let's go ahead and do that. First of all, let's find the mass defect before we go on to energy. So to do this, let's take 29.93676 and subtract 205.92945 plus 4.00151. Watch your decimals, guys. You're gonna have to insert this into a calculator as well, so you need to be really careful about how you write them out and type it in, because one single mistake and your value is off by 10-15 mega electron volts. So watch out. This gives delta M as 5.8 into 10 power minus 3 U. Now, let's use the conversion. 1U is equal to 931.5 mega electron volts and solve. So E is equal to 5.8 into 10 to the power of minus 3 U times 931.5 mega electron volts per U, which is equal to 5.41 mega electron volts. And that's it. Moving on to our next question, part 2. The polonium nucleus was stationary before the decay. Show that by reference to the momentum of particles, the kinetic energy of the alpha particle is greater than the kinetic energy of the lead nucleus. So first of all, since the polonium nucleus was stationary, P alpha plus P lead is equal to 0. So keeping that in mind. Now let's go ahead with E alpha. E alpha is equal to P squared by 2m alpha. And E polonium is equal to P squared by 2m polonium. That's it. Oh, sorry. We're dealing with lead here, guys. So 2m of lead. Let's go ahead and cancel out our p's. So since we know that P alpha plus P lead is equal to 0, we can assume that P alpha, the magnitude of P alpha is equal to the magnitude of P lead. Now, since we're squaring here, that goes away. So that means the ratio of E alpha to E lead is equal to 1 by 2m alpha divided by 1 by 2m lead. So cancelling this out, we get 2m lead. Let's cancel out the 2 as well. So mass of lead nucleus divided by mass of alpha is equal to energy of alpha divided by energy of lead. And since mass of the lead nucleus is greater than the mass of the alpha particle, this means that the energy of the alpha particle is greater than the energy of the lead nucleus. That's it. Now you'll need to write this a little bit more elegantly, add some more lines about how exactly it works to make sure that it makes sense to the examiner, like I've been saying the entire time. So moving on to part 3. In the decay of polonium-210, alpha emissions can be accompanied. Discuss how this provides evidence for discrete energy nuclear levels. So you guys might remember that nuclei can exist at different energy levels, and during decays they can change in energy level. So let's write this answer out and I will explain it. Alrighty guys, so to start off, let's go ahead with the first most basic statement. Since a photon is emitted, this means that it must have some energy, right? So this energy is related to its wavelength as E is equal to hc by lambda. So we've given our existence of energy based on wavelength. Now let's show how it provides evidence for nuclear energy levels. We're going to take from the question, all photons have the same lambda, right here. So they have the same energy. Since the photons are emitted when the nucleus moves from its higher energy levels to lower energy levels, this means that all the energy levels, since that means the energy levels are the same. And in fact, it means that the energy levels must be quantized, because if they're non-quantized, that means that you will have energies or photons with energy 1.52 or 1.61 and so on. But because they're quantized, we can with sufficient confidence say that the energy of the emitted photon is going to be constant. And that's what we have. And that's it, guys. So let's go on to part C of the questions. A sample contains 5 grams of pure polonium, and the decay constant is 210. Of polonium is 5.8 into 10 power minus 8 seconds, a second inverse, and we say that lead 206 is stable. We're given the time, 1 year, and we are asked to calculate the mass of lead 206 present. So to do this, let's start off with our values. So m naught is equal to 5 grams, lambda is equal to 5.8 into the 10 power minus 8 second inverse. And your lambda is your decay constant, of course. Now, here's where it gets a little bit tricky. We're going to use the molecular mass of polonium as 210, and with that we're going to find the moles of polonium, which is 5 by 210 mole. And I'm going to leave it like this for now. Maybe I'll switch it up later. And finally, let's take 1 year is equal to 3.1536 into 10 power 7 seconds. Or you can just do this by multiplying 24 times 60 times 60 times 365 in your calculator, and you get your answer. And since we're working with seconds over here, I figured it was wise to use seconds there too. Now, let's go ahead and find our undecayed mass. Undecayed moles, rather, not mass. Since we are working with two different nuclei, it's better to work with moles rather than grams, so that we can easily convert between them, since 1 mole of your reactant will form exactly 1 mole of your product. Chemistry students, you might be familiar with this. Physics students, not as much, but the concept still holds true. So that is equal to the initial number of moles, m naught, times e to the power minus lambda, 5.8 into 10 power minus 8, t, which is 3.1536 into 10 power 7. This is equal to 3.823 into 10 power minus 3 moles. Undecayed. Remember this, guys, it's undecayed. So, keeping that in mind, let's find out how much lead is present. So, moles of lead equals moles of decayed polonium, which is equal to 5 by 210 minus 3.823 into 10 power minus 3, which is equal to 1.998 into 10 power minus 2 moles of lead. Now, mass of lead is equal to moles into mR of lead, which is equal to 4.11 grams, which is approximately 4.1 grams, to keep in context with the two significant figures values that have been used here. And that's it. So, in question number 7, we are given a beam of monochromatic coherent light, and we're essentially given the single slit experiment. Part A of the question says that the intensity of light at point O is I naught. The distance OP is x. Here we're asked to sketch a graph of intensity versus distance. One thing you guys have to remember is that at your minimum point, at these P and Q, which is given as first minimas, your intensity is going to be 0. So let's mark that. And at 0, your intensity is going to be I naught. These are all given in the question itself. Now the important part is to note that even at 2x, it's going to be 0, because minimas occur at regular intervals. Now, to draw the graph, let's just draw a smooth curve from 0 to x. Perfect. Now, we are going to draw the curve from x to 2x. Now, you might be tempted to pull this back up, maybe make it a curve like this, and bring it back down. But you have to remember that after the first minima, the intensity doesn't reach more than 30%. So right here. So this is your maximum possible value. Now you don't know how IB examiners work. They might set it 25%, they might set it 20%. So safe bet is always just to keep it at around the 10 to 15 mark. Make sure it goes up and back down. That's it. So being able to do that means that your examiner clearly sees, hey, he understands that the intensity rises back up, but he also sees that the intensity does not rise back up to its full extent. Now let's move on to part 2 of this question. Early theories of light suggest that a geometrical shadow would be observed. Explain how the diffraction pattern forms provides evidence for the wave theory of light. Now this is the second question where we've had to show that a particular experiment and show how the output of that experiment proves a certain theory. So to do this, let's use the same thing. The maximas and minimas that are formed can be explained by the superposition or the interference of waves. So let's write this out. Like I said, since the pattern shows a diffraction with maximas and minimas, it can be explained with the superposition of individual waves, and this supports the wave theory of light. And that's it, guys. Not too much explaining, and we're only given like 4 lines, so try to keep it succinct and within your area. That's it. Let's move on to part 3 of our question. We're given the wavelength of light, the distance between the slit and the screen, and the width of the slit. We are asked to find the distance PQ. So this is P and this is Q. This is going to be your first minima distance, and this is going to be your second minima distance. Now just going ahead and like drawing on this makes it really easy to see that you might have an angle right here. So let's pull a quick diagram and draw that down below, shall we? So I'm just going to leave this in the corner over here so that we can show that we've actually done our work. And let's go ahead and try to solve. Since we've marked this angle as theta, let's first solve for theta. You'll see in your data booklet that we're given the formula theta is equal to lambda by d. And since we're given the d right here, which is 0.1 millimeters, we can try to solve for this. Lambda is 590 into 10 power minus 9 meters, and d is 1 into 10 power minus 4 meters. And this gives us a theta angle of 590 to 10 power minus 5. Not degrees, radians. This is very important because here we're using something known as the small angle approximation, which only applies to small angles lesser than about 1.5 degrees. And this small angle approximation is really useful when you don't want to like break out the calculator in your paper 1. So right here we're going to stick to radians, and this angle is small enough that we can just take it to be a direct value. Sine theta and tan theta are both equal to theta for such small angles. You can try this out in your calculator, it's really cool. And now let's calculate PQ. So since we're given our distance 2.4 meters and we're trying to find x over here, let's write out tan theta is equal to x by 2.4 meters. And like I said before, since we're using the small angle approximation, we can directly correlate that to 590 into 10 power minus 5. So we directly equate that. Now we can say x is equal to 590 into 10 power minus 5 into 2.4, which is equal to 1.416 into 10 power minus 2 meters. But we're not asked for the distance between P and O, we're asked for the distance between P and Q. So this means that PQ is equal to 2x is equal to 2.832 into 10 power minus 2 meters, which is approximately equal to 2.8 into 10 power minus 2 meters, sticking with our two significant figures, and that is our answer. Now let's move on. Part B of the question is a little bit more lengthy and much more explanation required. So I'll write out our answer and explain it right to you. So let's start off with the question itself. We're told that the single slit is the place with the double slit, and the width of the slit is the same as the width of the single slit. That's good for us. Outline how the intensity variation between P and Q will change. Pretty simple and straightforward. So I've started by drawing a neat little graph, that messy-ish little graph that shows the double slit pattern intensity over here. Now, one thing I've marked is this dotted line over here, which is kind of hard to see, but hopefully this makes it a little bit better. That dotted line shows the modulated single slit. Next, in a solid line, I've shown our double slit interference pattern. So the double slit pattern actually looks just like a curve with the same peaks, not at different peaks. But since we are considering the width of the slit in this arrangement, we are going to assume that the modulating arrangement does exist. There's one more thing that we have to consider. The initial intensity is going to be greater than our I naught. Now, I also wrote it out over here. So the central peak increases and a greater number of smaller fringes appear. Now this is all very clear on the graph. You guys might get full marks just for drawing that graph, but a verbal explanation never hurt anybody. But we have to mention that the minima will still be located at the same spots since it's modulated by single slit diffraction. Now, you could also talk about how the intensity is decreasing as it goes away, or any other points, but these are the core points that you have to remember and keep in mind while discussing double slit interference that is modulated by a single slit pattern. So let's move on to question number 7C. We're told that the light source actually emits two wavelengths of light, and the average wavelength is 590 and the difference is 0.6 nanometers. A student is attempting to resolve the wavelengths using a diffraction grating with 750 lines per millimeter. Remember that, guys. And that the incident beam is 2 millimeters wide. We're asked to comment on whether this diffraction grating can resolve the wavelengths. So the key term here is comment, which means that we have to do some calculations and make some assumptions, and then we have to provide a conclusion to the overall question. So to do this, let's start off by by writing out the values, as always. Lambda average is equal to 590 nanometers. Delta lambda, which is the difference between the wavelengths, is 0.6 nanometers. And the number of slits per millimeter is 750. And width is equal to 2 millimeters. So, first of all, let's calculate the number of slits that the light illuminates. Number of slits is equal to 750 into 2, which is 1500 slits. Next, let's use our Rayleigh criterion for light, which is R is equal to lambda by delta lambda. So this is 590 by 0.6. Now you might have noticed I am using nanometers here, but this is because it's a ratio, and if we were to write 10 power minus 9 and 10 power minus 9 here, they just end up getting cancelled out. So to save myself a step, I've done this. This gives us 983.333 repeating, and this can be approximated to 983 slits. Since the number of slits is greater than R, it can be resolved in the first order. Now, if it wasn't, then you might have to use a second or third order diffraction, or third order spectrum, sorry, to be able to resolve the two wavelengths. But since the number of slits is greater, it can be resolved in the first order spectrum. That's it. Let's go ahead and move on to question number 8. The diagram shows field lines for an electrostatic field, and X and Y are given as 2 points. Our first question here is, which of the 2 points has a larger electric potential? Now, really quickly, if you guys look at this, you might be compelled to believe that X has a higher potential than Y because there's a greater density of lines between them. I know I did when I was writing my exam. But what you guys have to remember is that lines flow from positive to negative potential. And since you see the direction of lines is this way, Y is actually at a greater potential than X. Now, to explain this in a written form, we first start off by stating Y is at a greater potential. Next, we move on by explaining how we know this. So, we can say that potential flows from greater to lower, higher potential, to lower potential, and the field lines flow from Y to X. And that's it. Of course, you could also maybe talk about how the potential is in the opposite direction of the field lines or anything like that, but this is the easiest for me and the easiest for me to think about, since fields has always been a really odd chapter for me. Might be different for you, but it's a very okay. Moving on to part B, a satellite is launched from the surface of the Earth into a circular orbit, and the following data is given: mass, height, mass of Earth, and radius of Earth. We are asked to show that the kinetic energy of the satellite is 2 into 10 power 10 kilojoule or joules. Sorry. Now, you could go ahead and straight out write the formula for kinetic energy of orbit, which is equal to gmm by 2r, which a very nice teacher of mine had us memorize. But you don't have to do this. You can derive this from our formulas in the data booklet. Let's start off with a v orbit, which is equal to root over gm by r. And let's plug that into a kinetic energy equation, which is half mv squared. Half times mass of satellite, remember this, times gm by r whole squared becomes gm by r, which is equal to gmm by 2r. Simple enough. Now, when we plug in our values, 6.67 into 10 power minus 11 into 6 into 10 power 24 into 8 into 10 power 2 whole divided by 2 times. Now, here's a very important part. You can't just write 6.4 into 10 power 6. You have to write 6.4 into 10 power 6 plus 5 into 10 power 5, which is 6.9 into 10 power 6. And this gives us 2.3 into 10 power 10 joules, which is approximately 2 into 10 power 10 joules. Hence, proven. That's it. Moving on to part 2. Determine the minimum energy required to launch a satellite. Ignore the original kinetic energy due to its rotation. Perfectly easy for us. So let's go ahead and start off our initial minus gmm by r. This is our potential energy at a particular point. And let's say we are adding delta E, which is our minimum energy. This is going to be equal to the total energy of the satellite in orbit, which is equal to the potential energy minus gmm by r plus h plus gmm by 2 r plus h. So this means that delta E is equal to gmm, so I've just taken that out as common, 1 by 2 of R plus H minus 1 by R plus H plus 1 by R. And plugging these values in, we get a delta E of 2.7 into 10 power 10 joules. That's it. Now I've simplified the answer already. I mean, you could have written 2.6625, which is what you'll get from the calculator, but to save a little bit of time, I'm just moving right ahead. You guys know this by now. Moving on to part 9, which I believe is our last question. No, we have one more question after this. A parallel plate capacitor of this value is made from two metal plates separated by an air gap of 1 millimeter. The capacitor is initially charged to a potential difference of 24 volts. First question, calculate the energy stored in the capacitor. Straightforward, E is equal to half CV squared, which, plugging into these amazing devices called calculators, we get a value of 4.32 into 10 to the power 8 joules, which is approximately 4.3 into 10 to the power 8 joules. As always, 2 SF. B part 1. The charge capacitor is disconnected from the voltage supply, and separation between the plates is increased to 4 millimeters. Explain the change, if any, to the potential difference between the plates. As always, I've written it out, and let's go ahead and discuss the main points. The charge stored between the plates remains the same, but since capacitance is epsilon A by D, where the capacitance must reduce because the distance increases. Next, by Q is equal to CV, we see that V is proportional to 1 by C when Q is constant. And as such, the potential difference between the plates is going to increase. And we can also give a certain value, since the distance is increasing by a factor of 4 and epsilon is the same, the distance between the plates must increase by 4 times. That's it. Moving on to part 2, determine the work required to increase the separation of the plates. Easy peasy. Let's look at the change in energy, shall we? Work is equal to delta E. E1 is equal to, as we calculated, 4.32 into 10 power minus 8 joules. Now let's calculate E final. EF is equal to half CV squared, which is equal to 4 times E initial. Now this is because your capacitance is decreasing by 4 and your voltage is increasing by 4, so this is squared, so C by 4 times 16V is equal to 4 into half CV squared. So I've done this calculation on the side and just input that straight in. Now this means that your final value is going to be 1.728 into 10 power minus 7 joules. Now delta E is simply going to be, we could also have taken delta E is equal to 3 times initial energy, but to make it more clear, we've gotten the final and we've got the initial. Just plug them straight into your calculator and subtract it. You will get 1.296 into 10 to the power of minus 7 joules, which is approximately equal to 1.3 into 10 to the power minus 7 joules. And that's it. Moving on to question number 9. We are given a graph and we are asked to draw the variation of time with current in the resistor in a RC circuit, which means resistance capacitor circuit. So obviously we are going to start at I0, and we are given tau, which is our time constant. So If you guys remember, the time constant is the time at which 37.5, I believe, percent of your capacitor has discharged. Now this might be a little bit more or a little bit less. So an easy way to check this is simply by going into your capacitor. Sorry, going into your calculator. So when you take the equation Q is equal to Q naught e power minus t by tau, correct? Yes, minus t by tau. The time constant is basically the amount of time it takes for your charge to become half. So 1 by 2 is equal to e power minus t by tau. This means that t by tau is equal to ln 2 and tau is equal to ln 2, which is 0.69. But this is while charging. While discharging, your tau is going to be at 0.3 basically. So perhaps we go a little bit. So let's say it comes right there. Yeah. So let's draw a simple smooth curve through the graph, and this is going to be easier on actual paper since actual paper has texture and doesn't react badly when your pen slips. Kinda. So a nice smooth curve that shows essentially an exponential decay from I naught to the final value of tau. And that's it. Now let's move on to part 2 of that question. A similar mathematical relationship can be used to model phenomena in other areas of physics. State an example of such a phenomenon. Like we said, this is exponential decay, and there are actually two things off the top of my head that I can think of. Newton's law of cooling, if any of you have heard of that, done an IA on it maybe, and the other one is nuclear decay, as always. So let's stick to nuclear decay because that's a safe option and it's very, very obvious. So let's go ahead and move on to the last part of this question. A diode bridge rectification circuit is often modified by adding a capacitor in parallel with the output. Describe the reason for this modification. Starting off, a capacitor is used to debounce the rectified current, and this debounce is an actual electrical term that's used, but in reality it's also known as smoothen, so that would probably be a better, more apt term, but in my head debounce just sounds way cooler. So is used to smoothen or debounce the rectified current. The absence of the capacitor would result in sharper peaks, and the voltage would drop to zero during the cycle, since the capacitor essentially stores energy during the bridge rectification circuit, and provides a smoother, more constant output, and it increases the overall efficiency of the circuit. Now I've written like 4 points here, which is more than enough for a 2-mark question. And as a rule of thumb, you always want to write at least 2-ish points more than what the marks allot for, in case you are missing some points or missing key terms in your actual answer. Now let's move to our last question. Question number 10. We're given a Feynman diagram and we're asked various questions about it. Number 1. Identify the fundamental force responsible for decay. From the question, we see that the exchange particle is a gluon, and a gluon is only responsible for a strong nuclear force. So let's write that out here. Strong nuclear force. That's it. Now, deduce, referring to a conservation law, that X is a quark anti-quark pair. So you guys should know the conservation laws: conservation of charge, strangeness, baryon number. So for this particular question, I'll be using baryon number. So since we are saying that the conservation of baryon number must be fulfilled, on the left side the baryon number is 3, and on the right side the baryon number must be 3. I made a statement saying that this, so this. Next, since the down, down and up quarks of the neutron over here account for the 3 baryon number, X must have a baryon number that cancels out. And the important point here is This is only possible in quark-antiquark pairs. And that's it. So the last question of this paper, guys, the energy released is in the order of 10 power 8 electron volts. Estimate, using the uncertainty principle, the mean lifetime of a delta baryon. Your data booklet comes in really helpful here, guys. So delta E, delta T is greater than or equal to h by 4 pi. So here we're given our delta E value, which is 10 power 8 electron volts, and we are asked to find delta T. So let's go ahead and answer that. But first, we need to convert 10 power 8 electron volts into joules. So 1.6 into 10 power minus 19 joules per electron volt, which is equal to about 1.6 into 10 to the power minus 11 joules. Now, let's plug that into our equation. 1.6 into 10 power minus 11 into delta T, mean half-life, is greater than or equal to h, which is 6.63 into 10 power minus 34 by 4 pi. Delta T is greater than or equal to 3.29 into 10 to the power minus 24 seconds. So the mean lifetime is 3 into 10 to the power minus 24 seconds. And that is it, guys. I hope this video made sense. This is my first paper where I'm actually discussing long answer questions instead of just numericals, and I hope it made sense. If you have any questions, as always, please post them in the comments below, and I will be glad to help you out. If you'd like any more help or any specific doubts, feel free to send me an email or send me a message on Discord, both of which will be in the description below. Have a great day, and the best of luck for all N22 students in your physics, chemistry, and every other examination. Goodbye.